What's that?
Are we still in class in
Yeah,
there?
March. Thank you. All right, March. Okay. I think we're all ready for a break. So where we're at is your next assignment is going to be just applying WMS to generate a HEC-1 model for a certain location and breaking that location up into subbasins. So that's what we're going to be going over in today's class. And so it's a repeat of the demo from today. And then I'm also going to ask you to create another guide for yourself. So the previous guide that you prepared included rational method, national streamflow statistics, and TR55. This next guide is going to be your step-by-step overview on how to set up a HEC-1 model. So you can skip through all of the steps related to delineating the watershed, running towpaths. Some of the outlines before skipped over how to calculate the curve number. You know, they didn't really have an adequate explanation or screenshots related to that process, which is a little bit Byzantine. So if your prior guide doesn't have a good outline on determining the curve number, you might include that for this HEC-1 guide. But for those of you who had a good guide up to and including creating a curve number, then this next guide could just start at, once you've got a delineated watershed with a curve number, what are the steps that you follow to initiate and start filling in the HEC-1 model? And then, excuse me, through the process of both exporting the runoff hydrograph to a spreadsheet, which we'll cover today, and then subdividing the watershed into subbasins. So everything that we're going to be doing today, create a guide for yourself. That assignment's going to be due the Monday after spring break. So you've effectively got all of next week to repeat what we're going to do in class today and make that step-by-step guide for yourself. So any questions about where we're at in the semester, upcoming due dates, or anything of the like? You can say here on Monday the 25th, we're not going to have a live class meeting. That will be a recorded video. And that's going to be some steps that are known as stochastic modeling. So I'm going to be showing you how you could do a lot of automated simulations with a variety of different precipitation depths, a variety of curve numbers, and kind of how to probe at some of the uncertainty that can exist when we don't really have precise knowledge on how much precipitation there's going to be or what the curve number is. We just sometimes have estimates of those things. So it allows you to develop the range of possible flow rates rather than just assuming it's a single flow rate that you're going to get. So anyways, that stochastic modeling lecture will be a video that I'll post early next week so that it's online, and I'll email you the link. I'll put the link to that in Blackboard, and then that's what we'll do instead of an in-person lecture for the 25th. All right. Let me give you this handout. Here's the watershed that we're looking at today. It's about 9 square miles in Morgantown. And what I'd like you to do is identify the outlet. I mean, you can tell sort of from the shape of the river, the location of the interstate. I think you'll be able to define the project bounds using that shape recognition. And then delineate the watershed. You can see what we want is this branch before it gets into the Monongahela River. If I say it slowly, I'll say it right. Monongahela. So we don't want to put your outlet in the river itself. If you put your outlet in the river itself, suddenly you've got tens of thousands of square miles. But if you have it, you know, several pixels upstream from the river, then that's going to tell us what the watershed that dumps into the Monongahela at that location, what its area is. I'd like you to calculate the curve number. In the handout I've just given you, you can see there's some blanks that you need to fill in, like what's the curve number based on the land cover and the soil type. fill in the blank for what's the 10-year runoff peak flow rate based on HEC-1. So I'm going to delineate the watershed. I'm not going to narrate through my steps. I'm going to delineate the watershed. I'm going to calculate the curve number, and then you do the same, and then we'll see if we get kind of agreement on the area, curve numbers, and then we'll go through the subdividing process together. line than this for your boundary. Like maybe it's more blocky than this, you know? Like each one of these is a pixel, and so, you know, if you find that it's more blocky, probably what that means is that you were more zoomed out in your initial view of the project area. If we go to the project bounds and see what was my view, I tried as much as possible. I like to zoom in as much as possible so that I'm only downloading the data that is relevant. And sometimes you don't know initially how far the watershed reaches to the west or to the south or something. So it can be an iterative process, but like if your view was like this and you're more zoomed out, then what WMS probably suggested was a 60-meter elevation data resolution, meaning that each one of those cells represents 60 meters by 60 meters square. And so the mesh is more coarse if you're zoomed out. Now you can override that, and it's fine to have the resolution that it suggests. It doesn't end up taking that much more download time. And given the power of today's computers, I think that you're going to be able to run Topaz without any trouble. If you even, you know, if it suggests 60 and you go for 30, it's going to be fine. You could probably even, you know, if it suggests 30 and you go down to 7.5, I think it would be fine. And you're always going to get a more precise delineation the finer your resolution is. And especially in flat areas, it's important to have pretty good attention on your boundaries. We don't struggle with that so much in West Virginia because the watersheds have so much relief. You know, everything is so steep, especially out in Morgantown, that the boundaries are pretty distinctive. So it's not like having to split hairs and delineate based on just small differences in elevation, but it's usually pretty obvious. Now let me ask you this, why is it, like, what does this black line represent? Like, what is the physical characteristic that determines the watershed boundary? What is it that, like, if we were to follow this black line, what does it share? Like, what is the common theme of this black line? Think in physical terms. If you were hiking, think if you were out here walking around, what would this black line be?
Ridge line.
It's a ridge line. So it would be like the flattest path you could find around the perimeter of the watershed if you stayed on the ridge line. Now, not everywhere here has the same elevation, so this black line isn't all the same elevation, but it's going to be much less elevation difference along that black line than if you were to, you know, cross down towards the creek. Then you'd go through big changes in elevation. So, like, I wanted to make the point that the elevation boundaries, it's not just a random thing. Obviously, it's not random because all of us have about the same shape. But, like, it represents something physical that's actually out there, which is the high point in the watershed, so that all of the water that falls within this area is draining to a common point. So when we dropped the outlet, when we put the little dot on that flow accumulation cell, it's asking the question, what are all of the connected cells where water flows to that location? So any raindrop that falls in this boundary is headed towards our outlet, just by virtue of connected elevations. All right, so we've got, mine says 5651 acres. Well, I guess it's 5651.56, and so 5652 acres. Some of you may have it displayed in square miles. 52 acres. And if it's 640 acres per square mile, then that would be 5652 divided by 640, 8.83 square miles. So somebody that had a 60-meter elevation like mesh, if that was, you know, like the more coarse resolution, what did you get for the area? I saw a few as I was walking around.
I got 8.87.
8.87 square miles. So not too different. Braden?
8.84.
8.84? Okay. Pretty consistent. Okay. Now if you double click and bring up the HEC-1 parameters, just to refresh what we went over last time, we have to define precipitation. So basin average is always my go-to. What we're assuming with basin average is we're applying the same depth over the entire watershed area. Rather than if we had actual gauge data, we might be able to come up with a weighted average. But this is just assuming everywhere in here is going to be assigned the same depth. And by get precipitation from Webb, we can choose, on the handout it says, let's look at the 10-year precipitation. So get data for the 10-year 24-hour, the mean 3.46. Here in Huntington, I think the 10-year precipitation depth was 3.63 inches for a 24-hour storm. So a little bit lower in Morgantown. Okay, then the second part of it, define the series, and that's where we say which temporal distribution to apply for a type 2 24-hour storm, because we have the 24-hour depth that we've just got from the NOAA Atlas. This is just assigning an intensity over time with the temporal distribution. So okay, it starts filling in the text file down below here. Loss method, it automatically has our curve number calculated. 69.1 was the curve number that I got. I would assume that most of you are pretty close, like within 1% of that. Anybody get anything over 69.5 or anything less than 68.5? So we're all within 1 unit of curve number, okay? And then unit hydrograph method, going to compute parameters with basin data, and the SCS method for the lag time. It's automatically reading the watershed slope, curve number, and length. Okay, 1.9 hours of lag time. So here in HEC-1, we could run the simulation. Last time I suggested that you edit the parameters and increase the number of, or in job control, increase the number of ordinates. You don't necessarily have to, but if we don't, when we run the HEC-1 model, what you'll see is that you'll get the peak in the hydrograph, but not all the way back down to the base flow returning to its original 0. So if we'd extended it from 100 ordinates to 150, then this would have maybe tapered the rest of the way down close to 0. But our peak runoff here is 1,035 CFS. So let's look here. Q10, according to HEC-1, is 1,035 CFS. And it's easy enough just for us to see what National Streamflow Statistics has to say. Although we're now in a different area, let's refer back to the map, because we're not necessarily in the Western Plateau anymore. Let's just make sure which region Morgantown might be in. I frankly don't know. Anybody know, is it Monongahela County? Yeah. Okay, so it looks like it still is in the Western Plateau, because, you know, looking at the rivers here, if we zoomed in a little bit on this image, so where is Morgantown in Monongahela County? It's, well, I guess we better be sure because we're on the border. Monongahela County, West Virginia. All right, so Morgantown's over in this corner, and we'll look at the picture. No, so Cheat Lake is in the other zone, but Morgantown And specifically, we're looking in this part of Morgantown, I think. It's still in Western Plateau. All right, so back to NSS. Let's just look and see what's the NSS model have to say for the peak runoff. We've got HEC-1's prediction. NSS suggests that we would have, for the peak flow, Western Plateau 2010, the 10-year runoff 1339. Q10 NSS 1339. In hydrology, we don't get bent out of shape by variation like this. I mean, this is a science of estimation and extrapolation, and so we'd be pretty happy with this level of agreement between two independent models. So that's great. You know, the fact that it's off by maybe 25 to 30% isn't going to make anybody bat an eye. But the whole point now is to look at subdividing the watershed. So what we could do is we could put in another outlet part of the way through the watershed and split this watershed into two. And the advantage of doing that is it could be that part of the watershed is relatively urban and part of the watershed is relatively rural. So if we just look at, like, let's pull up the online maps and maybe the street map and just try and get a sense for, like, in this mixed watershed, are there sections that are relatively urbanized and others which are rural? So if you look at the map, it seems like the western side of the watershed is where all of these neighborhoods and streets are, but then this northern panhandle section of it, the eastern part, is relatively speaking got a higher proportion of undeveloped land. So if we were going to split the watershed like right here, then we'd have probably different curve numbers in those two different sections. And you don't have to limit yourself to two. You could put in, honestly, as many subdivisions as you want when it comes to splitting a watershed. But just as a first try, let's do this. Let's add another outlet partway through. I'm going to delete this earlier hydrograph that we've already seen. So I'm in the hydrographs menu, delete all. So now that's gone. But into the modeling wizard and choose outlet locations. We've already got one outlet and it's going to stay there. When we delineate again, it will continue to use this outlet as one of the sources. But now click Create Outlet Point and then drop another outlet. You can see where my cursor is, just to the left of where this branch is coming in. So maybe splitting this stream segment. We want to put the outlet in the right spot on a flow accumulation cell. Okay, so let me close this. You'll notice it's got these lines here. These lines represent, like in a schematic way, the structure of the watershed. And this is showing a basin which is connected to a stream reach, and then that stream reach has itself another basin. So there's two basins, a stream reach, and then the main watershed outlet. So we're kind of creating a structure. And the advantage, besides having like two different curve numbers, the advantage of subdividing a watershed is now we could look at the hydraulic characteristics of this stream reach. Like we could say, how long is that stream? We could assign an n value to it, and then we could calculate how long does it take water to flow through this stream segment, and then delay the hydrograph that comes out of this eastern section of the watershed, delay it by the travel time, and then it joins the flow that's connected directly to the western watershed. So they call that hydraulic routing, where you're taking the travel time delay into an account. Okay, so I dropped the outlet, but I haven't yet subdivided. I didn't delineate watershed yet. So where I was I created the second outlet, and then on this next screen, I'm going to click Delineate Watershed. It's warning me that when you delineate another time, it's going to overwrite all of your previous data from the prior delineation. So, like in the model, the areas, the curve numbers, the times of concentration, all of that is going to need to be redone once we delineate another time. So that's the nature of that warning. Click OK. It's calculating. And then it's showing us the boundaries of those two watersheds. So we can see, here is the dividing line in black between the two watersheds. And so we've got this western one, and then the eastern one includes that northern section. We've got the area of each, but the curve numbers is set to 0. So we need to calculate the curve numbers again. So to do that, we can use the same process. We still have the same soil type coverage. All that soil type is there. And we still have our land cover database. And so we can just go into calculators, compute GIS attributes, and we're going to use the soil type coverage, the land use grid, our standard key, which assigns curve numbers based on the hydrologic soil group and land use description. Click OK. The report will take a little bit longer to generate because we've got two watersheds now, but it'll give us a separate summary for each of the basins. So basin 3B is the one on the right. No. It's the one on the left. Here's 3B. And then 4B is the one on the right. I don't know why it doesn't say 1 and 2, but basin 3B is the one on the left, curve number 71. So that was the one that I suggested probably was a little bit more urban. And then the one on the right, which was a little bit more rural, has the lower curve number of 67. So we're kind of honing in on which are the specific sections that are going to be generating more runoff. This is kind of like unconnected impervious area versus indirectly connected impervious area. If it had been the reverse, if this had been the more rural section or the more urban section, then it would be especially important for us to subdivide and take that into account. So go into the HEC-1 model. So just double click on the basin symbol and bring this up. What's tricky now is that we have more menus we have to look at now that we've got two basins and a reach in our our conceptual model here. So right now we're looking at basin 3B. If you click on basin data, it's saying 3B. That's the one on the left. So here's the area, 3.48. So we need to separately assign the precipitation to that basin. So get precipitation, get data. Oh, sorry, it's set on the 50-year right now. I need to switch it to the 10-year. Get data. We have to do the type 2 distribution. We're going to have to do it to both basins separately. There isn't a way that I know of to have it execute this in batch, because those watersheds are separated geographically, so they could have slightly different precipitation datas. Okay, so I've just defined the precipitation. Now this only applies to that western watershed. The loss method is already seeing the 71.5 that it just calculated. Unit hydrograph needs to be recalculated because it's the smaller basin. So compute parameters, SCS method, okay, 1.25 hours. All right. So those are the three things that I need to define for basin 3B. Now to get to basin basin 4B, I could either click done and then double click on 4B and it brings up, now you can see it's empty for 4B, or if I was still over here in the 3B basin, you can, these navigational boxes at the top, you can use to swap between either, right now this one is the reach, or if I click it again, then it takes me to basin 4B. So you can see down here at the bottom where it says 4B, you can just swap between the outlets and the reaches that way. So I want to look at 3B I've defined, 4B, and it kind of highlights it. You can see in gray the one that's selected. So again, I have to go through precipitation, get data with the 10-year depth, and then assigning the type 2 distribution. Loss method, it knows the curve number. Unit hydrograph method will calculate with the SCS. That's defined. Okay, so I've got both of the basins set up for a simulation, and now I just want to take the reach into account. And so the ways to do that is either I can use this select diversion tool and double click on the stream. I don't have very good aim. I'll just use that same way I was before with toggling between them. So the reach that I want to model is this one. So look at routing data. Let's see. So there's a couple of different methods here that you can put in the parameters of, like the slope of the channel, the length of the channel, the end value. So kinematic wave, for example, is one way where what it's already doing is it's calculating the hydraulic length from where we dropped this secondary outlet. If we follow the route of the water along this channel to our first outlet, you can see that the distance is 16,691 feet. So that's around 3 miles. That seems about realistic based on what we know, the scale of this being 9 miles in total, 9 square miles of area. So the flow distance is 5 miles. Now the slope is also calculated. The slope of the channel is about 1%. And then we can assign a Manning's N. And we'd have to send somebody out into the field maybe to do an assessment of what does that channel look like. You know, is it like a smooth clay at the bottom? Is it broken up rock and riprap on the channels? We'd need to have some information about what the channel looks like to assign a realistic N value. But in the absence of having that given to us in a report, maybe just we'll assume 0.025, which is maybe like a good baseline for a natural channel. But then the other thing is we have to, if we're going to say how long is the travel time delay through the channel, it wants to know the geometry of the channel as well. So you can either assume a trapezoidal section, a circular section, or you could define like your own shape of it. Let's just model this as a trapezoidal channel because that's pretty realistic for a natural channel. It's not going to have exactly flat bottom and exactly uniform side slopes. In reality, it would be irregular, but this is just so that we could get an approximation of the travel time. So if we had a survey crew or just from a site visit went down and we estimated that the average width of this channel maybe is 35 feet, and the side slopes are 1 to 1. You know, so Z is talking about what is the horizontal component of the side slope in a trapezoid compared to the vertical component. Click OK, and it's going to take the travel time into delay when next time we run HEC-1. So we're done now, and we can run HEC-1, run simulation. It's going to give us multiple hydrographs. It's going to give us a hydrograph for the basin itself, the hydrograph of the water as it enters the channel, and then the combined hydrograph, and then this is the hydrograph for just the western basin. So if you look at the western basin, has a peak of about 660 CFS. And if we combine like the main outlet, which has the western basin and the flow from the eastern basin, then the peak there is 1426. And then if we look at, here is the eastern basin as the flow is entering the channel. The time to peak is 695 minutes. And then here's the water as it's flowing through the channel. The time to peak is 810 minutes. So that's, I think, at the midpoint as the water is making its way through the channel. So it takes into account the delay of the time to peak. And in theory, we're going to have a more accurate idea of what this watershed is doing as we break it up into smaller pieces. And so remember when we just had a single watershed, the estimate was 1,035 CFS. But now that we split and subdivided this watershed and tried to account for the travel time and the fact that, you know, once the water gets into the stream, it's moving pretty quickly. So the flow is going to arrive maybe more suddenly at the outlet and with a greater peak flow than if we just modeled it as a single basin. So 1426 CFS is our revised estimate based on hydraulic routing. So you could break it up into more than 2 watersheds, and in fact there is a way that WMS, you can tell it how many watersheds you want, or like the maximum area. Let's see, if we go into the wizard here, it doesn't always work great. It does its best, but here in delineate watershed, subdivide basin. So ours was, I think, around 5,000 acres. And what if you wanted the maximum basin would be 1,000 acres? Subdivide watershed. It's warning us that if we do this, everything's going to be overwritten. But it looks at the watershed and it picks where would be the outlets if we were going to break it up into each one of them being no more than 1,000 acres. So let's see, we've got one here, one there, one here, one here, one here, and then one gigantic one. I can't believe that this is less than, what's the area there? Yeah, I don't think that it honored the, oh no, I was just subdividing this one, I guess. So I would maybe have to do it again. Probably the subdividing works best when you only have a single basin to begin with. If you subdivide and you've already got 2 basins, probably it's only going to apply it to one that you've got selected. But I did want to point out that here in the wizard, under delineate watershed, you do have the subdivide basin, and you could specify a maximum area, because there are some agencies, you know, like states or departments of transportation, that make recommendations on the maximum watershed area that you could include before you have to subdivide and start taking hydraulic routing into effect. So that would be an automated way to do it. All right, well, that's all the time we have for today. I'll put the assignment onto Blackboard, just the description. It's that you're going to go through this process at a watershed of your choice. subdividing it, taking the data from the hydrograph and exporting it. And if you don't remember what that process looks like, how to export the data like to a text file, let me just really quickly do that. I guess we've got 2 minutes. So I'm putting data into this panhandle section. And let me calculate a unit hydrograph lag time. Okay, I can run HEC-1 now, and there's only going to be one hydrograph, but that's all right. This panhandle model will have one. All right, so remember, if you want the underlying data, if you want this data, right-click, export/print, text/data, specify the location of the file that you want to save to. So we'd call it like exported data Friday.txt. Okay, and then the options that you want to select are change it instead of list to table, and instead of subset points, change it to points subsets, then export. And then this file that it just created, we can open up in Excel, and you could import it. It's going to be comma delimited. Where did I just save that? Exported data Friday. So here is times and flow rates in CFS. So that's how you could make your own spreadsheet and not just rely on the hydrograph picture that WMS provides. All right, that's it. Have a good spring break. I'll see you on Wednesday after spring break, because Monday will be a recorded lecture.